Hello and welcome to this Computer Science on Air Hangout called The Magic of Computer Science. Thank you to everybody who's joined us within the Hangout and the live stream today. I'd like to introduce you to Peter McCohen, who is Professor of Computer Science at Queen Mary, University of London. Peter's also co-founder of the Computer Science for Fun website, cs4fn.org, and today he's going to show us some magic tricks which you can use when teaching computer science to illustrate topics such as how programs work and how computers can search and sort information. During the presentation, if anybody watching the live stream has a question, please feel free to go ahead and post that into the G+ page underneath the video stream, and we'll look out for them so we can put them to the presenter on your behalf. The session is also being recorded, so you can watch it again afterwards. So now I'd like to hand over to Peter and thank him for giving up his time to present for us.
Hello everyone. So absolutely delighted to be here on Google Hangout. So as was mentioned, I'm Peter McCowen. I'm a professor of computer science, but I'm also an amateur magician. I've been interested in magic ever since I was a kid. And one of the things that occurred to me as I was developing through my academic career as a computer scientist, particularly an interest in artificial intelligence and algorithm development, was that from time to time I had those kind of epiphanous moments where I realized that some of the mathematics that I was actually encoding into my computer programs was actually very similar to some of the techniques, the kind of hidden secrets behind card tricks. And then it occurred to me, well, why not just actually bring these two things together and do something a little bit different? I mean, one of the difficulties with going into schools or teaching computer science is that sometimes it can be seen as being fairly dry, and particularly the more mathematical aspects of it become tricky to motivate students to be interested in. So what I decided was, rather than doing something with a computer, I would do something with these, which is a pack of cards. Because if you think about it, a pack of cards is essentially 52 different kind of data elements, and there's lots of different ways to be able to move those data elements around, kind of shuffling cards and so on. But in a magic trick, what you're actually doing is you're moving those cards around in a pre-controlled way, which is exactly the same as moving data inside a computer memory. So Paul Curzon and myself, when we created the Computer Science for Fun project, as part of that, as a kind of outshoot from it, I decided to start writing a couple of short articles on how the mathematics in a card trick can actually be the kind of mathematics that you can use inside a computer program. And from that arose a number of books which have actually been extremely popular, and they're available to download for free on the Computer Science for Fun website, which is www.cs4fn.org/magic. So we've got two books. This was the first one that we wrote, which is called The Magic of Computer Science, and the second one was called The Magic of Computer Science, Now We Have Your Attention. And that one specifically looks at kind of human factors in there. Magicians are constantly working out ways of being able to misdirect your attention, whereas actually a good piece of computer software design will ensure that people know exactly what they're doing at the right time. So actually, we have a research project that's looking at how magicians manipulate your attention, misdirect you, so we can understand what those rules are to allow the software development to prevent people from making those kinds of mistakes magicians want them to make. So if you've got the opportunity to download these and have a look at them, then I would recommend them. We've had them translated into a number of different languages thanks to our friends at Google, who've provided money to be able to do that. And it's an extremely popular and interesting way of being able to get people actually pulled into thinking about computer science in a different way, to think about the principles rather than worrying about the actual coding on a computer. So what I'm going to do now is to show you a little example of the kind of thing that I do. So this is an excerpt from one of the shows that I do. I go around schools, science exhibitions and so on, actually showing some of these tricks, doing it as a kind of full magic show. And what I'm in fact doing is breaking the magician's code, in that you should never reveal how tricks are performed. But I think that in the name of science, in the name of computer science education in particular, I'd be forgiven for some of it. I should point out, actually, these are all ethically farmed tricks. They're tricks that have been around for years and years and years, mathematical tricks. And what we've done is come up with a slightly different reworking of them. And one of the colleagues actually here logged on, Jody Gregg, who's a magician I'm working with in Scotland on a teacher's support book. He and I have come up with different ways of doing different presentations. And so a piece of magic is actually a lot like a piece of software, because there are two parts to a magic trick. One part is the secret technique, and the second part is the presentation. And without the two of those, then the magic fails to work. Now, if you think about it, there's a nice analogy in software. Software has the algorithmic mathematical background to it, but it also has the requirement for a good usable interface, good usability. So understanding how human beings work, how to entertain them, for want of a better word. And without those two parts working, again, the software doesn't do what it likes to do. So there's actually a very nice metaphor, I think, between developing good quality software and developing a good quality magic trick. So this trick that I'm going to do just now is one where it's been refined. This is a nice opener that I use in the show, particularly for a large group of students, and is based around a trick that some of you may have seen before, but some of you may not. And this is our kind of version of it. So what I'm going to do now is cross my fingers and hope that the technology allows things to do shifts in the way that I want them to shift. And I'm now going to share my screen with you and select window, and up goes the trick. Okay, so are we now all able to see my slides, hopefully? So the way I would start this is very similar to the way I started this, and explain that I'm an amateur magician and that I'm going to do some tricks for you. So there's a very famous trick in magic called the torn and restored card trick, in which somebody selects a card from a pack, you then tear that card up and make a magical pass over it, and the card is restored to its former glory. Well, as I said, I'm an amateur magician. I can do one half of that trick. I can do the part where you tear the card up. But I think that's probably less impressive than you would hope for. So what I'm going to do instead is I'm going to try a little bit of mind control on you. What I'm going to do is I'm going to show you some cards. I'm going to ask you very quickly to choose a card. And once you've chosen that card, don't change your mind. Just use the first card that kind of jumps into your mind. Remember what that card is and raise your hand. Okay? So again, instructions, I'm going to show you a card, choose one very quickly. There's a card here particularly that I think you'll all be drawn to choose. I think psychologically I've placed it in the right kind of a place. Remember that card, don't change your mind, and keep your hand up. And keep your hand up until I tell you otherwise. Okay, so here we go, here are the cards. Everyone should choose a card, hopefully everyone's chosen a card. Remember that card, okay? Remember that card, keep your hand up in the air. So I'm going to shuffle the cards. I'm going to shuffle the cards a little bit more. Now I'm going to tear up one card, and hopefully, if I tear up the card that you were all thinking of, you'll see a moment of amazement. Here we go. So I'm going to tear up the one card, hopefully you were all thinking about. If your card is not there, if it's been torn up, put your hands down. Here we go. So hopefully, I managed to get that, for some of you at least. So the question is, how did I manage to do that? Is it because I do genuinely have the ability to magically and psychologically manipulate you into all making exactly the same choice, or is there a trick to it? And at this point, I would then start to ask the audience, the school kids, what their thoughts were on there, and there's some amazing solutions people come up with, a lot of which are complete and utter madness. But nevertheless, a little bit of inquiry-based learning, a little bit of guesswork as to how it goes, and some of them can actually be very creative. But eventually someone normally will twig on this, and the answer to this particular magic is that all the cards at the beginning and all the cards at the end were in fact completely different cards. So if you select, for example, the 8 of diamonds, the 8 of diamonds isn't there at the end, so whatever card you choose from the first screen, its duplicate isn't there in the second screen. This is actually called the princess card trick. This is the mechanics of the trick. It dates back to around 1905. An American magician called Henry Harden developed it, and he used to do it with trick cards. This is my kind of PowerPoint-based version of it. But for me, what's important here is as much as the effect. And this is why magicians never reveal how a trick is done, because once you know where the elephant is hidden, once you know how the trick is done, the magic vanishes. And hopefully there were some of you at least who, for a moment, experienced a moment of astonishment. And that's what magicians love, is that moment where suddenly the world just seems more mysterious and interesting and exciting because of that. The mechanics for this is very simple, but actually the computer science behind it that makes it work is, for me, as interesting. So this is all to do with the way that the human brain processes information. So computer science, to me, is as much about how biological systems like brains process information as much as it is electronic systems. So the first thing to say is that I did choose these cards specially. These were specially selected cards. There is no obvious card in there like an ace of spades or a queen of hearts. They're a mixture of suits and they're fairly high values. What I then do is I put you under pressure. I tell you, you've got to choose a card really quickly and not change your mind. Of course, it doesn't matter if you change your mind or not, but it puts you under more pressure to believe that. So I show the first set of cards, and what you do is you choose a card. So for example, you choose the 8 of diamonds. I then tell you to put your hand up and remember that card. Now, at that point, you've no idea what I'm going to get you to do later. So you'd better remember that card. I could be wanting you to come out the front of the class and dance on a table singing Yankee Doodle Dandy and explain what the card was. So you'd better remember it. So your brain focuses on the task at hand, puts the processing power into that. It remembers that card and it approximates the rest of them. It says and the rest are 7, 8s, 9s, and there's a mixture of different suits and different colors. I then use something called time misdirection. Magicians use this absolutely all the time. I put time between you having memorized the card and having to then recall the card later. And that bit about shuffling and shuffling more puts enough time in there that even if you did remember some of the details of those other cards, you're constantly having to go through a refresh in your brain, going 8 of diamonds, must remember 8 of diamonds, and you forget the details of the other cards. So finally, at the end, when I show the other cards, and your card isn't there, you look for the 8 of diamonds and it's vanished, there's a torn up card, there is a logic to that, there's a story, there's a narrative, and I do seem like a respectable professor of computer science. I'm telling you, that's your card I've torn up. The magic is complete, the story is completed, the brain sees a completed pattern. And that's in part what gives this trick its strength, is the fact that you are paying attention to one thing, i.e. the value of the card you're remembering, and you don't notice that the other cards have actually changed. So the next question is, what does this have to do with your MP3 player? And again, I use this as a throw-out question. I ask the kids, what's it got to do with it? Some of them are suggesting something to do with shuffling. It's nothing to do with shuffling. Somebody even suggested that you could tear up an MP3 player, which I've frankly found rather a scary prospect. But nevertheless, it's nothing to do with being able to tear it up. After a little bit of time, some will spot it, others won't, but then you put them out your misery. And in fact, exactly the same trick that I played on your eyes is being played on your ears every time you listen to an MP3 track. Because MP3, I then go on to explain, is a data compression algorithm. MP3 is the audio compression algorithm that's used in the audio layer of MPEG. And that uses an idea called psychoacoustic encoding, a very big word for a very simple idea. And that is, if you understand the way the brain operates, the brain listens to sounds, and if it hears a particularly loud sound, it tends to pay attention to that and to ignore quieter sounds that are occurring around it. So in the same way that you paid attention to the card you were remembering and didn't notice the other cards around it had actually been changed in the final slide, similarly, your brain is paying attention to the loud sound and isn't noticing the fact that you're taking out all this other data from quieter sounds, which allows you to actually compress the music to make it much smaller and fit onto your little mini player. So in fact, inside each MP3 player, there's a tiny computational model of the way that your brain's auditory cortex, that part of the brain that processes sound information, works. There's a little bit of artificial intelligence built into that, which allows you to be able to listen to compressed music to take that music and use small amounts of data to produce the same sorts of sounds where you're not actually spotting where the difference is. So although that trick involved cards, it actually has applications in audio processing. I then, because I'm involved in doing work in this area, do a very quick run through some of the research I've done. So this I'll just briefly go through on here, building a computational model for something called visual saliency. If you're looking at an image, you can see that there are certain parts of that image that are far more likely to be of interest to a person. And so I've been working with a PhD student of mine to actually model the way the brain works mathematically and to be able to test it. So here, for example, there's the road sign, and over on the other side is an image that shows how the computer has actually scored those images on the basis of its saliency, of its importance. So clearly the red triangle kind of stands out there because it's a much higher score in there. And obviously it's a useful thing to do. It's only part of the way that human brains see, but I'm able to pick up these ideas and use them in robots to build vision systems for robots that mimic the way the human brain works. So what the system can also do is it can take an image and I can ask it to select and rate all the different parts in that image, and I can ask it to remove a part of the image, for example, that would be very easy for you to spot had been taken out, and another part that would be far more difficult for you to spot. So something that's got a high saliency rating, you should spot fairly quickly as changed. Something that's got a low saliency rating is something you find more difficult. And this is something called a change blindness paradigm, and it's used to study the way that the human brain operates. And it turns out our brains are processing so much data all of the time that we actually don't have the level of awareness of the world around us that we think we have. And so these are a couple of examples that I show as brain experiments. Again, nice because the whole class can be involved in doing this. So I'm going to show you the first brain experiment where I've asked the computer to remove something that is fairly obvious, hopefully that you'll spot has been changed fairly quickly. And in the second one, something that should take you that little bit longer. So again, the instructions, and I go to the class, is have a look at this. There's a flashing image, something is changing in that image. When you spot what's changing, don't shout out loud, just put your hands up. And we'll see how quickly the group gets it. And so here we go with the first one. So you're looking for something that's changing. My computer predicts you should get this one fairly easily, fairly quickly. So here we are. And normally at this stage, there are a couple of hands that begin to go up around the classroom, a couple of hands more, until eventually most of the class get it reasonably quickly. And for those of you watching at home, the answer is if you look on the road sign, you'll see the number 98 is appearing and disappearing. So that was rated as being a fairly high level saliency for the computer program, and therefore when it extracted that, it was expecting that you would be able to spot the change fairly quickly. This second one is a more difficult image. Again, I've asked the computer to rate the different parts of it for the computer saliency in there, and told it to remove a part that actually you should find fairly difficult to spot that it's changing. So my computer predicts that you'll take longer to spot this. So actually what you're doing with the class is doing some real research. You're actually getting data from an experiment with these computer-generated stimuli and using their brains as part of it. So it's a kind of an active learning experience. So in the second image, again, what's changing? I asked them to put their hands up, not to shout out, and see if they can spot what's changing. So again, for those of you at home, have a try with this. What we tend to find is that fairly slowly, hands will go up, certainly not as quickly as previously, because this is more challenging. Some people will not actually get this in the time that you're willing to give in the class to do it. So for those of you at home who haven't spotted it yet, if you look at the bottom of the image, at the tower block on the left-hand side, you'll notice that the whole front of that building is appearing and disappearing. Now that is a really big change, and yet because of the way that our brain processes information, it's tending to pay more attention to things like the river and so on, and less attention to the detail in the kind of low contrast regions of the image. So this is a very nice way of being able to show that computers can actually simulate the way that our brains work, and here's a kind of live experiment that you can run in the classroom with students actually around that. And then I finally mentioned in there that if you're interested in seeing some more of these kind of images, this was a student project, which is a kind of spot the difference game, which at the moment is available for the Android. And what you do is you use these images generated by the computer, and you have to spot where the changes are against the clock. And again, it's free to download, so if any of you are interested, the Android market, it's there. If you go along to qappsonline.com, which is the spin-out venture that we created here at Queen Mary for student projects and various other bits of research that are being done here that are created as apps. You can download that for free and find out some more about the science actually behind that change blindness. It appeared on BBC and various other websites and media outlets across the world. So what I'm going to do now is switch back, hopefully, to my Google Hangout. And am I switched back? Not yet. There we are. So I'm back in the room. That's a kind of exemplar of the sorts of things that I get up to. And hopefully in the next series of these sorts of hangouts, I'm going to show you some card tricks that you can use to teach some of the fundamentals of computer science. But I thought that I'd do the kind of what was the beginning of the act. It gives you an overall feel of the sorts of things that can be done. And those slides, again, are available if anyone's interested in them on the Computer Science for Fun website. Okay. Are there any questions that came in during that as a matter of interest? Jody, would you'd like to say something about using computer science magic to teach? Can you click Jody onto the full screen? Okay.
Hi folks, I had to take it off mute.
Can't I hear
yeah, just going on what you were saying there, Peter. That particular lesson, to try and create more classroom activities, one of the ideas that we spoke about was to create an opportunity where students could create an animation of the card effect that we just watched, in terms of being able to put up a picture of the first cards in the slide, followed by the time delay, followed by the cards being shuffled, and then eventually the other cards. So I think that lends itself really well to create an animation and for students to understand what makes the cards cognitively not salient, what cards to choose. For example, if they were to use 5 cards that were all black and labelled 1, 2, 3, 4, 5, and then use red cards labelled 6, 7, 8, 9, 10, then clearly that effect wouldn't work. So by creating an animation, not only is that hands-on sort of practical activity, but by choosing the right cards, they're also demonstrating the ability or the knowledge about saliency and what's important. So that was one of the lessons, Peter, that we spoke about in terms of developing that idea.
Yep. Yeah, absolutely. Just for the record, Jody actually is a teacher, computer science teacher, but he's also an award-winning magician. Spookily enough, actually he won the award from the Forth Valley Magic Circle, which I was one of the founder members of when I was a kid back up in Scotland. So he contacted me, and well, what could I say? You know, it's kind of an old alma mater kind of a thing. But that book will be available hopefully fairly soon, which ties it into actual curriculum for excellence in Scotland. But nevertheless, I think that there are elements of that would work across the various curriculums in the UK, the US, and across Europe. And the one thing that Jody's been able to really add to this, as well as a creative, magical brain to it, is actual kind of classroom testing experience, combined with a knowledge of how to tie that into the curriculum. And I think that one of the things that we found, certainly in the UK, and I suspect maybe the same in other places, is that having something where there are easy to use packages of kind of work plans of things that teachers can pick up quickly and be able to use them where they're tied into a curriculum, where obviously you're being assessed on how you're delivering that curriculum, is actually an important part of trying to make more of an impact in classrooms with the kinds of stuff we're doing at CS for Fun. And that's why we partner with people like Jody as a teacher who has a knowledge of these things. that are in there. So hopefully that will be something that will be of interest more broadly. Okay.
I've got a question that could be for either Peter or Jody, or maybe both. But imagining that there might be teachers out there who want to begin using magic tricks and think that they might like to use magic in their classroom, but maybe haven't done magic before, or not since they were a kid or something. What's a good trick to begin with that's kind of easy to pick up, but gives good results in class?
Jody, would you care to, from your experience, what's the one that you think is easiest? And I'll give my view on it if it's different from yours. What do you think?
I think the easiest one to begin with would be Carry On Conjuring, because there is, like all the tricks in both your book and the new book, there's no sleight of hand, there's no difficult move.
There's nothing difficult. And
I think that was certainly the key principle for myself. Was it's all very well as a magician to create tricks and perform tricks, but teachers aren't magicians. I think it's absolutely crucial that all the tricks are easy to learn. And I believe that all the tricks are easy to learn. There is no sleight of hand, difficult moves, as I said. Carry On Conjuring requires nothing more than a very simple setup, which takes 10 seconds, 15 seconds to set up. And then it's just a simple process. How teachers want to present that and what words they say whilst presenting it is entirely up to themselves. But yeah, the important thing is that these effects are really easy for teachers to learn, because I know teachers are already overworked and will complain about not having enough time. If you're to provide them with complicated tricks that require a lot of learning, then they're not going to bother. Yeah. So easy to learn.
So all those materials and things are available on the website if you're interested in that particular trick. Another one that I is really simple to do is something called the piano trick, and that one involves a very simple algorithm and a lot of discussion around things like usability and deliberately confusing user interface. And unfortunately, I noticed that we're very short of time, and maybe I'll do the piano trick as the starter for the next one. But again, if you're interested, there are a whole load of videos that I've done that are linked to from the CS for Fun webpage that actually show you the tricks being done with live audiences, and then I explain the mathematics and so on that's behind those. So there's a nice way of being able to pick up on those, as well as the kind of discussion that we're having here in more kind of formal videos that are available.
So thank you very much, Peter, for that great presentation. Thank you also, Jody, for your insights there. Just to remind everybody who's watching the live stream, this broadcast has been recorded, so you can watch it again and share it with colleagues. You'll find it on youtube.com/edu@Google, as well as on Google's Education on Air website. Also, keep an eye out on the Education on Air website for more computer science hangouts for teachers, and we hope to see you again soon. Thanks very much, and good evening.